All right, welcome ladies and gentlemen. This is the video number one in the first half of the periodicity, or I should say electron structure and periodicity unit. So this is focusing a bit on electron structure. In this video I'm going to be talking about paramagnetism versus diamagnetism, those two terms, and what is this thing called the penetration effect, which sounds dirty, but I swear isn't really. So first up, paramagnetic versus diamagnetic. Now these are terms that have to do with the electron configuration of an atom or an ion and how that affects their magnetism. So diamagnetic are elements that have all of their electrons, quote, spin paired. What does that mean? It means if you consider the sublevels, for example, we have maybe S and P. Spin paired would mean that in each sublevel, you have electrons with both an upspin and a downspin, meaning they are spin paired. You have two electrons. Basically, it's a fancy way of saying you've got two electrons in the subshell. So these are spin paired electrons. If you have all six of your electrons in the p subshell, those would all be spin paired electrons. So the elements that exhibit this have to have all of their sublevels and therefore all of their orbitals filled. So things like helium, beryllium, neon, these are elements that their atomic form is diamagnetic. What does that mean if all of their electrons are spin paired? It means that these elements are not affected by a magnetic field. Species that where all their subshells are filled, where they've got two electrons per orbital, are not impacted at all by the magnetic field. And the opposite of that is paramagnetic, and these elements now do have an electron that's in an orbital by itself, so all of their electrons are not spin paired. An example, if we just had S, an S subshell, if you just had one electron in it, this would be something that is not spin paired. That electron is not spin paired, meaning it doesn't have the down spin electron in there too, basically meaning there's just one electron. And these elements will be attracted in a magnetic field. So that's a really big point. This difference in the electron configuration actually leads to different impacts in terms of the magnetism of the species. And then this next one is just showing you a diagram of some other examples. Found this figure online, thinks it's a pretty good one. We've got the silicon, in this case, is a bonded silicon, so it's not quite the same as the silicon on its own. But in this case, well, we're going to talk in our bonding unit about what that means, but all of the orbitals are in fact spin paired, so that's what you really need to pay attention to. So this is diamagnetic. Likewise, in NaCl, when the ionic bonding has taken place and we've transferred that electron from the sodium to the chloride, now the sodium, everything is spin paired, and the chloride, everything is spin paired. So again, non-magnetic, diamagnetic. Versus paramagnetic, iron. Iron's always the big example, right, when people think of magnetism. These are our non-spin paired electrons that are going to cause it to be paramagnetic. Next up, the penetration effect. This is getting at the reason why electrons have the certain configuration that they do, and what's the order for filling. For filling electrons when we are looking to determine something's electron configuration. Different sublevels have different energies, and that's really a massive, massive point. And the penetration effect shows why that is. So a 2s electron, we say, penetrates to the nucleus more than an electron that would be in the 2p subshell, or an electron that's in an orbital in 2p. What does that mean? We're going to look graphically in terms of location, what that means, but then also in terms of energy. If the 2s electron can get closer to the nucleus, can penetrate more to the nucleus, it's going to mean that that 2s orbital is going to be more attracted to the nucleus, and more strongly than 1 and 2p, which will then give the 2s orbital a lower energy than the 2p orbital. Different subshells have different energies, and it's due to this thing called the penetration effect. It's due to where the orbitals are located and how close they can get to the nucleus. So With that in mind, this figure right here, which I have in color but you don't, shows distance from the nucleus on the x-axis and probability, right? Where is this orbital, where is this subshell most likely to be located? Where are we most likely to find it? That's essentially on the y-axis. So notice that the 2s is in red and the 2p is in yellow. And if you're only looking here, it looks like the 2p is actually closer to the nucleus, right? Because its peak is here versus the peak being here for 2s. But what the 2s orbitals do that the 2p orbitals do not do is this. A small percentage of the time, it is more likely to find the 2s orbitals in this super close distance to the nucleus versus 2p. And this right here is called the penetration effect. The idea is that the 2s orbital is quite literally penetrating almost through some of this, 2p area right here to have a chance of being found closer to the nucleus. Remember, this is all about probabilities. We don't know for sure. That's quantum mechanics. We cannot say for certainty. Based on the calculations that go along with the wave function, which describes different possibilities, different things about electrons, where can you find them? There is a chance, although it's a small one, of finding the electrons in 2s much closer to the nucleus than the electrons in 2p. And that chance, even though it's small, gives the 2s electrons a significantly lower energy because they are going to feel the attraction of the nucleus much more strongly when they are in that super close location. You're saying, but what if they're not there? But we don't know that they're not there, right? We don't know that they're not there. Quantum mechanics is all based on uncertainty, and we have to go with the fact that there's this chance that they're going to be close, which gives the 2s orbitals a lower energy. What's the big takeaway if you're sitting here being confused about probabilities and quantum mechanics? The takeaway is what you need to know. 2s is going to be closer to the nucleus and lower in energy than 2p, and it's due to this thing called the penetration effect. So now we're looking at 3s. This is the 3s orbital. And now you'll notice we have these two basically new smaller bumps and then this one larger bump right here. And so this one is our most probable distance from the nucleus for electrons that are in the 3s orbital. But there's, again, this likelihood, this penetration, that this chance that we can find the electrons in 3s a lot closer to the nucleus than their most probable location, which is, back here. This gives the 3s electrons a lower energy. This fact that there's a possibility of finding them a lot closer. They can sort of penetrate through some of the other sublevels in energy level 3. And that's what this figure is showing. We have 3s, which is in red, 3p, which is yellow, and 3d, which is purple. Or if you're colorblind, then you just look at where I pointed with my marker just now. And what this is showing is that, in fact, 3p, which is this line, can actually penetrate a little bit, whereas 2p doesn't. But it can't penetrate as much as 3s because this is the 3s penetration right here. And then we have 3p. And then we're going to have 3d right here. So what is this telling us? What is the big point? It's telling us that 3s has a chance of getting closer to the nucleus than 3p does, and 3p has a chance of getting closer to the nucleus than 3d does. So what does that mean? It means that 3s is lower in energy than 3p, and 3p is lower in energy than 3d. That's the takeaway. And that should be somewhat intuitive because we are talking about writing electron configuration. We're going to be talking about writing electron configuration. This is going to be important for us there about filling s electrons, an s subshell first, and then filling a p subshell, and then filling a d subshell. So there is a relative energy, right? 3s is lower in energy than 3p, which is lower in energy than 3d. And then likewise, if we were to go to energy level 4, we'd see the same effect in terms of 4s is lower in energy than 4p, which is lower in energy than 4d, which would be lower in energy than 4f.